All right, if there's no question, then let me move on to the topics for today. So today we will learn about how the computer boots, starting from BIOS to bootloader to the kernel. And in this regard, we will also handle some of the histories of the x86 CPU because we are learning some of the archaic legacy mode of the booting. And then many students are curious about we are living in the UEFI era. So I'm not sure you have heard about UEFI, so universally extensible firmware interface, which is the new technology that they replace the BIOS. But the reason why we need to learn about the BIOS is the UEFI is internally doing this kind of stuff. Yeah, and then I believe if I don't teach the details of the BIOS in this class, and after you getting a job and then working on the industry, then you might have no time to learn about that. So I want to teach that in this class. Yeah. So let's take a look at how JOS works first. So I want to show that the JOS, even if it is in a virtual environment, it mimics all the hardware features. So you can virtually feel it that you are developing the operating system for the bare metal machine. So suppose this is an OS/2 server. So it runs with Linux. So it has a Linux kernel, and then it has its own hardware network interface, and these can CPUs and on. And then you can regard this icon as yourself. And then what you are doing is connecting to the terminal of the OS/2 server. So it will be going through the network interface. Yeah. And then JOS environment is actually inside of the QEMU. So the QEMU stands for Quick Emulator. And then why does it called as an emulator is that it emulates a CPU, disk, graphic card, and network device, all the hardware devices as a software. So even if they are running as a software, they are virtualizing everything. So we are running JOS apps and then kernel in here. So those kernel and apps will virtually feel the same have the same interface to interact with these kind of the virtual hardware. And then even if they are connecting to the real hardware, they will use the same interface. So what QEMU does for us is actually virtualizing all the hardware. So even if we are developing JOS apps using QEMU by interacting with the terminal, so the JOS and you will feel the real environment of the developing the operating system on the real hardware. Yeah. So all the actual operations of the disk and then network or graphic card stuff, yeah, that will be interacting with the OS/2 servers, the Linux kernel, and you can see that the result over the network. And this is just a brief description of the JOS. Any questions? All right, let's move on to next. So let's try to learn about what the computers are doing when you push the power button. So I'm not sure, have you ever seen this kind of screen? Yeah. So the modern computers that start with the Dell or Apple mark, and then they are actually hiding this kind of this screen at the background. Yeah. But internally, what they are doing is the computers don't know what kind of hardware configurations you have. So for instance, the Apple's MacBook, it only has the very few variants so that they can configure it for their own way. But think about a general PC. In that case, we can choose any kind of CPU. If the motherboard is for Intel, then we can choose any kind of the Intel CPUs. And then we have freedom to configure how much of the RAM we would like to plug in and use. And then we can also have freedom to what kind of SSDs or NVMe or even disk hard drive. So we can connect to any kind of devices. So the computer don't know what kind of devices are there. So what they need to do is they need to run BIOS, which stands for Basic Input Output System. And then what it does is like it checks about like what kind of devices are available in the system and configure it before booting the system. So if you get into some of the setup of the BIOS, then like there are some of the features that you can turn on and off. And also you can disable some of the hardwares and then configure some of the, which one is the boot device. Yeah, you can do that kind of low level configuration. And this BIOS is very important. So if the BIOS information got lost, so for example, in the motherboard of your desktop computer, there's a chip. That's the read-only memory, which stores BIOS information on your motherboard. And then, so the configuration part of the BIOS is stored into the volatile memory. And then that volatile memory is somewhat persistent because your motherboard has a very small, thin battery inside of it. So if you ever take off the case of your desktop and then take a look at that, you can easily find some of the very thin CR2032 battery in it. And then the purpose of that battery is to store these kind of configuration of the BIOS. But if that gets lost, then you will see that this kind of error message and you need to configure it again. And because if that kind of information got lost, you cannot boot. So some of the good motherboards supports a dual BIOS. What it does is like it try to back up some of the default configuration, and then it will restore from there if you get like a battery loss or like if there is some situation of it, or if you get some of the lightning and like that gets into your computer, then your BIOS got like they've completely wiped out. So in such a case, like this kind of the dual BIOS might help if the lightning does not burn the entire like of your BIOS, the motherboard. And then after this kind of the BIOS setup step, what it does is, so power up and then BIOS initializes the devices, and then the BIOS. So to do this kind of stuff, BIOS actually need to put the code to RAM to run it by CPU. Yeah. So at the start phase, your RAM is completely empty. Yeah. And then CPU does not know how to start. And then what BIOS need to do is, after initializing the peripheral devices, BIOS will put the initialization code from the BIOS to the RAM to the specific address at the physical address FFFF0. Yeah. So the reason for using like this kind of the low address is that like the computers in old days, they are only support 1 megabyte of memory. And then the 1 megabyte is actually 100000 in hexadecimal. So 1 megabyte minus 16 is actually in this address. Yeah. So like I'm not sure why they picked like this kind of address. So it's somewhat matching number. Yeah, but it is within the 1 megabyte of region. So they put the code from the BIOS to the RAM in this address, and then make CPU to run on that code address. And then the main purpose of the doing like this kind of code is that like it will also initialize some other peripherals for this specific CPU or something. But the most important thing is that like the BIOS need to boot the device, need to read the boot sector to load the operating system afterwards. And to do that, what the BIOS will do, so there's an example for that. So because the BIOS put the code into FFFF0, and then like so when you run the QEMU NoXGDB, yeah, and then attach GDB on your QEMU for the JAWS, you will see that your CPU is stopped at the specific address FFFF0. So the reason for this is that the QEMU's virtual BIOS is actually operating the same way as the hardware BIOS does. Yeah. So that's why it is stopped at there. And then if you follow the code starting from here, then what you will see is that like it will read the first sector from the disk, which is so-called boot sector, and then put that onto the another specific address 7C00 and then run it. One question.
Is that address is that like universal across all motherboards, or is that gonna vary depending on the BIOS chip that's on the motherboard?
So to answer your question directly, this is a fixed address for across all the BIOS, but there is no reason to choose 7C00. That's the magic number. We can actually change it, but when the engineers try to standardize the thing, yeah, they just fix that address. Yeah, that's why. Yeah. Any other questions? And then some of you might be curious about like the GDB says that the target architecture is assumed to be i8086. Then what is i8086? So i8086 is Intel's like the first computer, first 16-bit computer, born in 1978. Yeah, and then it runs with 5 megahertz of the clock. That was a super fast speed at that era. So now we are living with the 5 gigahertz or 6 gigahertz CPUs, but in 44 years ago, yeah, that was the state of the art. Yeah, and then now you guys are playing with the 64-bit register CPUs, but at that era, 16-bit was plenty. Yeah, so like and then the reason why our BIOS start with the CPU as a i8086 is just for backward compatibility. Yeah. So they designed the BIOS to be used for the universally, and then the Intel designed their CPU to support even for the 32-bit CPUs, they need to support 16-bit, and then even for the 64-bit CPU, they need to support the 16-bit one. And then that kind of having backward compatibility was not that having much overhead and hardware. So like the Intel designed the CPU like that, and then BIOS designers are designed their BIOS like that. And then they can automatically enjoy the backward compatibility. And that's why if you choose like the putting in legacy mode or a BIOS mode, even in like the computers in current era, yeah, they can support starting from i8086. Yeah. And then even if like our OS2 server runs with his Intel Xeon, I believe like this one is like the 4th or 5th generation core Xeon server version of that. And then even for that CPU, that has the mode with the 16-bit real mode, which is a mode to run in i8086. And then the next thing is, so although the address is FFFF0, the address shown on the GDB is somewhat different. And then like the F000 colon FFF0. Yeah. And then what is that address? So I told you that the CPUs in this era only uses the 16-bit, registers. But suppose you are addressing memory with the byte granularity, then like how many of choices can we have with the 16 bits? That's 2 to the 16, so 65536. So that's like around the 64 kilobyte. But even for the era of the 1970s, 1980s, 64 kilobyte was too small to be used in computers. Yeah. So like they would like to support at least 1 megabyte of memory. Yeah. There was an engineering decision. So at that time, like even for like the 1 megabyte of memory, yeah, that could cost like $200 in that era. Yeah. But like the important thing is like the engineers would like to support 1 megabyte, which requires a 2 to the 20 bits to address 1 megabyte of the memory with the byte addressing, even with the 16-bit registers. Yeah. So the one easy way to do so addressing 20 bits with only with the 16-bit registers is that use 2 registers. Yeah, that's easy. So that's why we are using 2 pairs of the 16-bit. So here, one hint for like the reading hexadecimal numbers and then interpreting hexadecimal number easily is that like you can regard each digit represent 4 bits because it's a hexadecimal. So 16 variants can happen in one digit. So 0 to 9, A, B, C, D, E, F. Yeah. And then like because like these are 4 digits. 4 digits, each digit represents 4 bits. So 4-digit hexadecimal number represents a 16-bit number. So we have two 16-bit numbers, and then to indicate the address FFFF0, the syntax is like we need to have like the sum of the upper address as F000 and then lower address as FFF0. And then I will explain what each number means and then how can you get the number FFFF0 as next. So it is so-called memory segmentation. Yeah. So the technique allows we are only having 16-bit registers, but it allows to us access 20-bit addressing. Yeah. And then how can you do that is like using 2 registers. So the value comes in front is so-called the segment register. And then the value comes after the column is the regular register. So right now we have a code address, and then code segment is stored with the CS register, code segment CS. So the CS register value is F000, and then the instruction pointer, the address that we are executing some of the code is on FFF0. So it is so-called the CS register and then instruction pointer. And then for the F000, FFF0, for that address, we are having the CS segment as F000 and then instruction pointer as FFF0. And to calculate the 20-bit, the actual address for the physical memory, what we need to do is like we need to multiply the first register by 16 and then add the regular register value. And then if you think like multiplying 16 is quite complex, that's not complex in hexadecimal numbers. So for decimal numbers, if we multiply 10, what we need to do is just adding 0 at the end. So the same thing happens for this hexadecimal number. So for the hexadecimal number, multiplying 16 means that we are adding 0 at the end of this one, and then adding the rest. That's why. So we will have F0000, and then for the rest of 4 digits are 0. So we just attach these 4, then that's the address. So that you can follow how I calculate that by doing this. F000 becomes adding 1 more 0 because we need to multiply 16 for the first one, and then adding the rest. Then it's quite easy to calculate the final resulting address. So first one, multiply by 16, segment register, multiply by 16, and then add the rest. And then resulting address will be 5 digits, and then each digit in hexadecimal represents 4 bits. So 4 bits, 5 digits. So we will have a 20-bit addressing. Yeah. So that's why like the 8086, the 16-bit processor can access the 20-bit of the memory addressing because the possible address range is from 0 to FFFF inclusive. Any questions? Yes.
So like we are using like 2 16 bits.
Yes.
And processing at 20 bits.
Yes.
So there's like a 12-bit ways.
Yes.
So how do they deal with this ways?
So like we can technically support 32 bits with the 2 16-bit registers, but the problem was like at that era so 32-bit means that we can addressing up to 4 GB, right? So at that era, 1970s or 1980s, there's no gigabyte RAM at all. And then engineers at that time completely ignored that, like our technology will develop like this. Yeah.
So they just ignore the 12
Yes.
12 bits.
Yes. They just ignored it. Yeah. So they are very practical. Yeah, they don't care about like what will happen in the future and then just develop it. But they realize that, that's the bad engineering practice. So from like the 1980s, 90s, yeah. So most of the engineers are thinking that like have you heard about the Moore's law? So that there is a Gordon Moore is like the founder of the Intel, and then like that guy once said that like the semiconductor process will get doubled in every 18 months or something. So like it will grow exponentially, yeah, as time goes by. So it's before the era of like the Moore's law, because the 8086 is the first CPU, yeah. So after that law came out, the engineers are thinking about like the RAM size can be exponentially grow, so we need to be reserved for the those kind of bits. But at that era, there was not. So the segmentation is, this kind of segmentation is used only in real mode. And then the reason why it is called as a real mode is that at the first time it comes out, this was the only mode. But later on, this mode has a limitation that we can only access 1 megabyte of memory. So even for the MS-DOS era, 1990 something, yeah, they might need like a 4 megabyte of memory, at least for running the game Doom. Yeah. So like the real mode is not enough for this kind of mode is not enough for the running general purpose. Yeah. So that they added a lot of the other modes, so-called protected mode, long mode. So later we called it as a real mode. Yeah. And for the sake of having the backward compatibility, all the x86 processors from now on, even for the Core i7 or 9, yeah, they all support the boots in the real mode. Yeah. And then like in lab 1, if you have started lab 1 already, so you have seen some of the keywords, so-called the protected mode. So we are turning on the protected mode because our JOS will not running only in 1 megabyte of memory. We will have either 128 or 256 megabyte of memory later. So we need to enable the protected mode, but we will learn about that later. Yeah. But the important thing is like in the real mode, the segmentation works like segmentation register multiplied by 16 and adding the offset. Then let's do a little bit of practice of the address calculation. So what will be the address pointing to from like this segment and offset pair? And then that's quite easy. So multiply this by 16, adding 1 0 and add, so 13333. Second thing, this is also easy, BB7FF, right? Just adding 1 0 and add it. And then a little bit of tricky thing. So it has a 0001. Yeah. So it's not that tricky. So what we need is like multiply this by 16, so 0010. So it's not on the 5th digit, but adding with the offset, so we will get 0111. Yeah. So the rule is multiply by 16 and then add with the offset. And then another tricky thing. What if the value is F8 and then the offset is 8001? Then F8 multiplied by 16 is F8000. Then adding 80001, then it will get over the 1 megabyte. Yeah. So 100001. And then the reason is like this is a hexadecimal number. So F8 plus 8 is like the 100. So that's why we have a carry out at here. Yeah. But don't worry about this. We have some of the techniques to handle this kind of address, and then we will learn inside this lecture. So please memorize that the real mode segmentation is segment multiplied by 16 plus offset. And then the reason why I'm keep repeating of this kind of thing is like that this will be shown on page 1. So please be familiarized to this kind of notation. And then now you can completely understand this kind of the address. And then the first code is having a long jump, segment register F000, and then offset value E05B. And then now you can answer where this code jumps to by calculating the segment address. So multiply by 16 and then add the offset. Then the target address is FE05B. So if you run the next instruction on GDB, actually the SI, step into, then you will see that the resulting address is FE05B. And then that instruction compares value 0 with the CS register offset 6AC8. So from the GDB dashboard, you can get the value of the CS register. So that's F000. And then to calculate the target address is that the F6AC8. And then you can take a look at the value. So that value is 0. And then the instruction wants to compare the value 0 to that. So you can expect that the result is true. Yeah. Any questions with the use of the segment in the first boot sequences? Yeah, it's just an easy calculation. Yeah. And then next is booting from the disk. So what BIOS does is like try to initialize all the peripheral devices. And then the next important thing is we need to boot the operating system. And to do that, so engineers in the very early days, they try to take a very easy and simple path. So what they are doing for the boot is that they set the boot sector, so-called master boot record, as the first sector of the disk. So you can regard the disk, even if like it was like a circular magnetic disk or like the NVMe kind of the memory. So you can virtually regard like all the disk space as an array of the sectors. And then what it does is just to read the first sector, 512 bytes, and then run it. Yeah, that's it. And then the only thing that they are checking is that the last 2 bytes of the boot sector must be 55AA. Yeah. And then if that condition does not match, then it will the computer will show that it has no proper boot device and then boot failed. Yeah. If you have ever seen like this kind of message, then either you did not plug the disk, or your disk is available, but its master boot record and does not have like the 55AA or some correct boot sector on it. Yeah. And then what BIOS does is like it will put the boot sector to the physical address 7C00 and run it. And then as one of the students asked the question, says the address 7C00 was specified arbitrarily, so that we can change it. But the problem is like the engineers would like to still get some sort of a standard. So that's why we use that address. And then you can actually take a look at how the boot sector look like. So if you run make in your JAWS directory, and then try to print out the just boot sector from the object boot that binary program. And this program XXD, so what it will show is like it will show the binary data of the boot record in a hexadecimal numbers. So that we can see that like all the boot sector contents in here, but at the end we can see that 55AA. So that's the signature of the boot record. And then maybe some of you have questions about why 55AA. Yeah. So I tried to decode the 55AA in the binary numbers, and then it is something like 100010101010 is repeating, and then so I'm not sure about the exact reason, but maybe the engineers in the early stage, yeah, they would like to detect any kind of the bit flips or errors. That happens, then they would like to stop the boot because like some of the bit flip happens in the middle of the boot sector, then it may damage the machine. Yeah, so they put like this kind of the alternating bit patterns for that. So I'm not actually sure about that, but that might be my conjecture. That is my conjecture. Yeah. And then what it does is like the BIOS will put this at 7C00 and then run it. So starting from this one, like it will store the code that like you will code in boot.s. Yeah, the assemblies will be compiled as a binary data and then stored in the boot sector. And if you are curious about like how BIOS is actually working in there, so one way is like you can follow the assembly in exercise 2. Yeah, as stated in exercise 2, you can follow all the instructions. But the good thing is that the QEMU uses the C BIOS, which is an open source BIOS. So if you click the link on it, then you can get to the point that like the code that shows that like how it loads the boot sector on the RAM. So the beauty of the being an open source is like we can take a look at the source code. So on the GitHub, you can see this kind of the part of the function. So it says boot disk, and then it set the boot segment as a somewhat 7C0, and then set the boot instruction pointer, and then boot segment. And then if we just follow the calculation, the boot segment is starting with this number, and then boot IP is so getting the last 3 digits and then shift 4 means like multiply by 16. So the boot IP will be 7C00. And then because the boot seg is a 7C0, and then it will be ended with the F000, then there's no 4th digit 0000, so it will result in 0. So it will completely ignore boot segment, but it will boot with the boot IP, which is the address 7C00. Yeah. This is the part that the BIOS actually sets the 7C00 as the address, and then put the boot sector in there, and then whole boot entry will jump to that code. Yeah. And then what does the boot sector need to do? So I told you that it only has 512 bytes. It's a very small code. Yeah. And then take a look at the operating system kernel of the OS2 server. So this is the one of the file. And you can see that this VM Linux Z. The Z means here is that the kernel is compressed with zip. Yeah. So the zipped code size is around the 6 megabyte. And then I try to unzip some of the Linux kernel. It shows up as a 24 megabyte or something. So 24 megabyte versus 512 bytes. So that we cannot fit the kernel entirely in the boot sector. Yeah. So what bootloader need to do is that, so the restriction is that in the real mode, we cannot use the memory over 1 megabyte. So as I told you, modern kernels are several megabytes. So we need to turn on some other mode, so-called the protected mode, to get access to the higher memory over the 1 megabyte. So the bootloader need to do that. And another thing is that the bootloader need to load another part of the OS. That's so-called kernel, the core of the operating system. So the concept is that bootloader is very small. It is only 512 bytes, but the last 2 bytes need to be 55AA, so that we can only use 510 bytes. And then with that 510 bytes of the code, what we need to do is we need to enable protected mode and then read the OS kernel code from the disk and load that to the memory. And don't worry, we can do that. And that's why you can use the computers, and then like that kind of engineering still survives in the world. Yeah. So the next is more about the x86 memory and protection. So for a few history about the Intel CPUs, starting with the Intel 8086, they developed the 16-bit computers, but at that time, they felt that like the 16-bit computer is too overkill. That's why they developed the 8-bit computers 2 years later, 1 year later. Yeah. And then they get back to another 16-bit computer in 1982. But the important thing here is that all these CPUs are supporting 20-bit addressing and only with the real mode segmentation. Yeah. And then in 1982, Intel developed the 80286. That's why like the so 86, 186, 286, 386, 486. That's why like Intel CPUs are called as a x86. And then we are still using the kind of the x86 architecture for Core i9, Core i7 CPUs in this era. Yeah. And then for like a 286 computer, because there was a need for supporting the bigger memory, yeah, they need to support the 16 megabyte of addressing. And then how can you do that? Is that they developed the so-called protected mode. The problem was that they do have only 16-bit registers. So we need to use the same pair of the segment and then offset kind of thing. But segment multiply by 16 and then add the offset, it only allows a 20-bit addressing. And to enable 24-bit addressing, what they developed is like the sum of the indirection table. So what that means is that in the real mode, segment register need to be multiplied by 16. But in this protected mode, what we will have is like this kind of the data structure. So we can set the base address as a 24-bit and then limit as the length of that region. Yeah. But just thinking about the base address, so what we will do is there is a table of the data, and then we will put the base address at 0, base address at 8, base address at 16 or something like that. And then what we will do is we will refer to that base address with the segment register. So in the protected mode, there is a no multiply by 16 at all. So what we will do is that we will use segment register. For example, if the segment register value is 100, then we will search for that table and then fetch the base address, which is 24-bit, from the 100 index of that table. So there's a one level of the indirection to get the base address. And then technically, what we are doing is, what this CPU is doing is splitting all the 16 megabyte of memory in 64 kilobyte chunk. And then we can refer to that by the base address. Yeah. But some of you might not understand what's going on here, but don't worry, we will not use 80286 protected mode because it's an intermediate one. And then the reason why I'm explaining this is that this is the first showcase of the protected mode in 286. And then the reason why it is so called the protected mode is that, so in this kind of the 8-byte structure, there is a bit flag, so-called the DPL, data privilege level. So what that means is that in the real mode, there is no memory protection at all. Any program can access any kind of memory region. Yeah. But I told you that like even if you run kill QEMU on the modem machine, you cannot kill the other user's process, right? So that kind of thing is protected by the memory isolation. And then to support that kind of thing, we need to have the notion of the memory protection. And then the origin of that memory protection comes from like this data structure from like the used by 80286. So I told you that there is a sum of the table, list of the tables, and then segment. We'll select that. And then from that table, the CPU will honor all the data privilege level and then the others when accessing the memory. So right now, you are not clear about the data privilege level, but when we get to the lab 2 part, which is like the next lecture and then the lecture in the coming weeks, yeah, you will be more clear about like how we protect the memory with this kind of flags. And then later, Intel developed the 80386 in 1985. Yeah, so the CPU is 37 years old. And then the CPU is born in the same year when I was born. Yeah, so it's a 32-bit processor. Yeah, so they developed the 32-bit processor in around 40 years ago. Yeah, and then 32-bit here means that 32-bit register, if it is byte addressable, then it can support up to 4 GB of memory. but around like the 128 megabyte of memory is plenty for this supercomputer kind of thing. Yeah, in that era. So at that time, they even don't think about like they support like that kind of big memory, but they develop the computers like that. And then to support the 32-bit addressing, so they changed the base address 0 to 15, 16 to 23, and 20 to 31, which means that they store all 32-bit base address to the table. Yeah. And then they also have these kind of flags. What that means is that like we can also set the memory privilege level. Yeah. And then we will learn about the details of this kind of table, so-called the global descriptor table, in the lectures, in coming lectures. One question.
What was the size of the table?
So the size of table is just 8 byte. So this numbers indicates the bit 0 to 15, 16 to 31, 32 to 63. So it will be composed as a 64-bit structure. So like the table size is 8. And then if you recall it correctly, I verbally told that the table as an index is a 0, 8, 16 or something. The reason for that is like each table size is 8 byte. And then you will be much more clear when you get to the lab 2, because you need to play with this data structure to enable the protected mode and then virtual memory for your JAWS. Yes.
Why are they breaking up the base? Why didn't they put base together?
So for the humans, it'll be better to have like all the bits all together, right? Yeah. For the hardware designers, they don't care. Like at that era, the cost of the hardware design is much more bigger than supporting for the developers or something. So like the data structure is designed for hardware, not for the human. That's why. So I'm not sure about the exact details, but with that data structure, Intel CPUs are more easily or more performant for accessing the bits. Yeah. So i86 protected mode, that's the mode that we are relying on up to now. So it is also used in like the 486 and Pentium 2, 3, but starting from Pentium 4, they supported 64-bit CPUs. But you will learn about the virtual memory and the page table later. So having a bigger address space is actually indeed incurring some of the overhead. So in these days, we are not using 64-bit memory address space, because 64-bit is like the 18 petabyte or something, right? So we don't need that memory yet. So right now, most of the CPUs are in the operating system are stick with like a 48-bit addressing. So they can support up to 256 terabyte of the memory. So that's quite plenty. But recently, starting from Coffee Lake, is 7th generation of the Intel CPU, which is released in 2017, I believe. Yeah, they support 57 bits of the address space for like having a future proof. Yeah. Yeah, so that address spacing can support up to 128 petabyte, but it will be extended to 63 bits, maybe. No, I believe this is the maximum bits that they can support, because this add by 9 is like the 66, right? Yeah. So and then like if we need more memory than the 128 petabyte, then we might need a 128-bit registers for the CPUs. And then next is about showing the boot memory layout. So when BIOS comes in, so the early engineers define that which area of the memory will be used for some of the fixed component of the hardware and software. So to have an easy design, they reserved the address A0000 to C0000 to this kind of the console video adapter. Yeah, so that we cannot use that space except for the playing with the video. And then for this kind of the C0000 and F0000, each of the 64 kilobyte chunk will be used by some of the devices. So when you plug in I'm not sure you have heard about sound card. So in the very early machines, so nowadays, like all the machines are equipped with the audio, like the kind of thing, yeah, on motherboard. But in very old days, there's no audio feature at all. And then we need to purchase the sound blaster or ad-lib sound card. And then if we plug that kind of things on the machine, they will use like this kind of the device area for the memory accessing. And then the BIOS will use the memory, the very top, the 64 kilobyte. So starting from F000 to 1 megabyte. Yeah. And then all the low memory starting from the 0 to 64 kilobyte area, yeah, that is free for use for the operating system and applications. Yeah. And then have you heard about the rumor that like the Bill Gates once show up that like that they say 640 kilobytes are enough for the general computing or something? I'm not sure like, if that is too old for you guys. Yeah. So when I was young, like that was like a kind of joke that like we are living in the era for like need for the more memory, but the Bill Gates just want to sell about like all the MS-DOS because MS-DOS only supports the 640 kilobyte of memory. But the history says like that's just a rumor. Yeah, Bill Gates told everybody that he never told about that. But that was a joke that like the Microsoft MS-DOS was so popular in that era, even for supporting like this kind of the small memory. So yeah, it turned out to be a rumor. But I just want to let you know about like there is a period that like we are restricted with that small amount of memory. Yeah. And then what BIOS does is it will put the BIOS code into FFFF0, which is almost the top of the memory here. And then it will put it will read the master boot record from the disk and then put that onto the 7C00, which is free for use for the operating systems and applications. And then what our operating systems need to do is we need to enable protected mode to enable the memory over the 1 megabyte range. And then we can load the kernel and run it. And then so I just visually described about this kind of step, but you can actually take a look at the code for all the operations. So if you want to skip the BIOS execution, then you can just set a breakpoint at 7C00 and then continue to run it on GDB. Then it will stop exactly at the 7C00. And then this is the code from the boot.s. So you will see that exactly the same code shown up here, but don't worry about like having no width. So XOR W means that W is word, which means 2 bytes. That means like it will operate on the 16-bit registers, but our GDB will assume that our initial start stage is I-8086, which is a 16-bit computer, a 16-bit computer. So that's why like that kind of width is missing it here. But you will see that XOR, move, that kind of the semantics are all the same on the GDB screen. And then next is about 820, but we only have 5 minutes to the lecture finish. Then I will describe it as fast as I can. Yeah. So after loading the bootloader, the first thing it will do is like the enabling 820. So what 820 means is that please recall that how we operate on the segmentation. So we need to multiply the segment register by 16 and then add the offset. Yeah. So this is fine, but take a look at this address pair. So it will get over 1 megabyte address, but in the very early CPUs, there's no memory over the 1 megabyte. Yeah. So it'll be an overflow, then computers cannot process it. So 820 means that the address bit for 20th bit in address. And then the reason why mentioning about 20 is that, so if we have this kind of overflow, then what that means is that like so each digit represents 4 bits in hexadecimal numbers, 1, 2, 3, 4, 5. So 20 bits are there. And then if the index starting from 0, that carry will be at the 20th position of the address. So what A20, address line A20 means is that whether to enable, whether to honor that bit or not. So that in the very early computers, because there's no memory over 1 megabyte region, so even if the 20th bit comes 1, then we will completely ignore that. Then we can use the segment register in the circular fashion. What that means is that if there's an overflow like this, we will ignore this 1, and then we will regard this address just a number 1. The tailing part. Yeah. So that's the thing. So if we set A20 as always low, so the masking that as a 0 bit, then even if we have an overflow, then it will go back to the low address like that. And then the reason why we have that is that one of the engineering implication of doing that is like by doing so, we can use the both end of the memory. So take a look at the address. The BIOS is residing at the first place. That's the FFFF0, which is the top of the address. And then what we need to put about the bootloader is the 7C00 is that here. But if we use these two addresses with the simple segmentation, then we need to change the segment. What that means is like we need to learn long jump to switch the segment back and forth. But what we can do is, if we can set the segment address as F800, then the offset 7FF0 will be translated into the FFFF0, which is the top address. And then if we put the same segment address, but the offset as FC00, then it will result in 7C00, then we can point to 7C00. So what that means is like we don't have to change the segment, but at the same time, we can access the top address and then bottom address at the same time. So it's a little bit more performant than like the switching the segment back and forth. So it's very early day engineering. Yeah. But the problem of doing that is like we don't need that. So we need to enable it first. Yeah. So that's why, because like we cannot use that kind of the bits, then like they will lose like the addressing of the 50% of our memory. So what just bootloader need to do is, so BIOS will read the first sector and load the bootloader. And then bootloader within the 512 bytes, we need to enable A20. We need to enable protected mode and to use the memory over 1 megabyte. And then we need to lead the kernel ELF. ELF is for like the binary file for the kernel. And then we need to do that all in 510 bytes. And then we will learn more about that in next lecture. Yeah. Thank you for paying attention. And then feel free to ask any questions because I will be here for 5 more minutes.